In this lecture, we're going to review and pick up from where we left off in the previous one in terms of the variance and standard deviation. Now, in order to calculate the variance and the standard deviation, what we do first is we set up a table of our data. So in this example here, here we have 9 students that took an exam. We'll call it a midterm exam, a multiple choice exam, scored out of 41. And so you see a range of different scores obtained by the students. And the first step here, in addition to indicating the sample size, which would be n equals 9, we then would calculate the average or the mean. And the average score here, we just take this to one decimal place, is 28.9. Now we want to examine how far away these scores are from the average. So we want to come up with one value to do that, and that's the standard deviation. And so in order to do this, the first step is to calculate the deviation score for each person. And I've calculated the first 2 right here. So to calculate the deviation score for the first person, you see the first person scored 34 out of 41. And just looking at the numbers, this number is higher than average. The average of 28.9. So the first step is to see how much this score deviated from the average. So we set up our column and our table. That's just deviation, which is x minus x bar the symbol for the average. So we just simply take that person's raw score and we subtract the average of 28.9, and we find that the first person deviated from the average 5.1 points from the average in terms of the raw value of the midterm exam. The next step is to then square this term, which is to multiply it by itself. So 5.1 squared equals 26.01. We now move to the second value of 22, and we can see that this student scored 22 out of 41, which is less than the average. And we just follow the same order as we take the 22, we subtract 28.9, and we keep the negative sign, and we see it's negative 6.9. So the negative indicates that it is less, the magnitude of this number is less than the average. We then square this value, so we multiply negative 6.9 by itself. So the parentheses indicates that we square the entirety of whatever's contained inside the parentheses. So we have to make sure that we go negative 6.9 times negative 6.9, which comes out to a positive 47.61. We then continue this for all of the entries in the table down to the 9th person, and then we eventually will sum up or add up all of the squared scores, and then we call this final value here the sum of squares. And the sum of squares is the numerator in the previous equation in terms of calculating the variance. So we would then divide this value by n minus 1, or 9 minus 1, which is 8. And that would give us the variance for these data. We then would take that score, take the square root of it, and then that is our deviation score as a plus minus. So we would therefore conclude that whatever our standard deviation score is, we would conclude that the standard deviation is plus minus the value from the mean of 28.9. And so when we take a look at the standard deviation with respect to the normal distribution, the standard deviation will capture approximately 68% of the scores in that distribution within plus minus 1 standard deviation unit of the mean. So for example, if we have a sample of, if we were measuring the age of people living in a assisted living facility, of our sample, we might find the average age of the residents was 80, and we might have calculated a standard deviation of plus minus 5 years. So note that the standard deviation value will have the same units as the average. And if those data distribute in a normal way, so we'll just assume that the data follows a normal distribution, we would see that the average of 80, x bar, is located on the x-axis at the line of symmetry if it is normally distributed. And if we add and subtract 5 from the average, we would have 75 in terms of subtracting and 85. So the 75 and 85 represents the standard deviation, the one numerical value that captures the variability of all the data in our sample. Now, if we use these limits, the one standard deviation limit, then the area underneath this curve, if we were able to paint this area, that will equal approximately 68%. And if our entire sample of people that were part of this calculation was 1,000, if the entire sample was 1,000 people, then one standard deviation, plus minus 5 years around the average, would capture approximately 680 of those 1,000 people. Now that means approximately 32% of the scores lie outside of plus minus one standard deviation of the mean in the tails. So we have a smaller number of the sample that are younger than 75 and a relatively smaller sample that are older than 75. The next question is, how does the shape affect the standard deviation? Because the standard deviation would still be calculated the same way, the plus minus one standard deviation would still capture approximately 68% of the scores in that distribution. So the same rules apply here, where about 68% of the scores are still plus minus one standard deviation. The only difference is that the scores would be just closer to the mean or further away from the mean. So what we see here on the left-hand side is a leptokurtic distribution where the scores are not as variable, or the ages are not quite as variable. So we take a look at the bottom here. We have the average age of those 1,000 people that is 80. Now this sample of 1,000 might represent a different assisted living facility. And the notable difference is that one standard deviation is 3 units above the average and 3 units below the average. So plus minus 3 years. So although the standard deviation is closer to the average, it still captures 68%. If the distribution in a third assisted living facility of 1,000 people was platykurtic, then we still have the average, we might still have an average of 80 years, but since it's platykurtic, the scores are more variable and are spread out further. So in this case, we have a standard deviation of plus minus 8 years. So 8 years less than 80, 8 years above 80. And the same rule applies here in that this captures about 68% of all the cases in this entire sample. Now, remember, the standard deviation is quantified in the original units. So if this is 80 years old as an average, 83 years old represents the upper limit of one standard deviation. 77 years old represents the lower limit of one standard deviation about the mean. So it's always in the original units. Another way to quantify variability, with interval or ratio data is what's called a coefficient of variation. And the coefficient of variation is calculated by taking the standard deviation of a sample and dividing it by the average of the sample. So if the standard deviation, using one of our previous examples, was 5 years, around an average of 80 years, it's important to note that the units, years divided by years, will cancel. And then that will produce a ratio that does not have a unit of measurement. We multiply it by 100%, and that puts it in a percent. So the coefficient of variation quantifies the variability of the which is quantified by the standard deviation, as a percent unit. And so the coefficient of variation does have some advantages in that it's unitless. It's independent of the units of measurement. And what that allows us to do is that then allows us to compare variability between different measures if those measures have different units. So we can compare variability between age, and we can compare variability between caloric intake, which is measured in calories. We can't compare them directly because age and caloric intake are measured differently. It's comparing apples and oranges. But if we calculate the coefficient of variation, we can now compare the variability values. And that's done because the variation is expressed as a proportion of the average value. So it gives us a measure of the relative variation, and that allows us to compare different measures. One final way to quantify variability is through what's called a z-score. So a z-score is a transformation of our raw data and our calculated statistics. The calculated statistics, of course, being the average and the standard deviation. So we can take any individual score. So if we have a sample size of 30, we have 30 unique scores. Each score can be converted to what's called a z-score, provided that we know the mean and the standard deviation of that group. And the z-score is calculated using this equation here, where we take an individual score, this is just one person out of 30, we subtract the average, and we divide it by the standard deviation. So note that if this was age, we come up with a deviation score in the numerator. So if the first person's age is 75, and we subtract 80, we would get -5 years. So the subtraction doesn't eliminate the unit, we still have years. And we have a standard deviation of, let's say, 5 years as well. If that's the case, then we have years divided by years, the years eliminates, and the z-score for each person is now unitless. And that allows us to come up with what's called a z-score that enables us to better locate the data with respect to the average. So once again, the x represents a single raw score. X bar represents the sample mean or the average, and S, usually lowercase, but in this case I used uppercase, is the sample standard deviation. So does the z-score provide some advantages? And it absolutely does. So the first advantage is that it allows us to evaluate the relative position of each unit in the sample. So not only will this allow us to compare the position of one case in our sample or one unit in our sample to the average, we'll also be able to compare the position of one score to another individual score in that within that sample. And it also eliminates the unit of measurement. So this allows us to compare between different outcome measures or different dependent variables. So this has a similarity to slide 34 with the coefficient of variation. But make note of the difference is that for a sample of 30 people, we will end up with one coefficient of variation for the entire sample. That was slide 34. But we will end up with 30 z-scores, one z-score for each person. It looks similar because we're eliminating the units, but the coefficient of variation, we get one numerical value for the entire sample. We get a z-score for every case in the sample. So this ends our second video here to close out our descriptive statistics.